Today's lecture is exploring kind, and it is on magnetic monopoles. You see, so far we have discussed about magnetic field arising out of a current or a solenoid, and what we have said is that the smallest unit giving rise to magnetic field is a dipole. Right. For example, if you consider a small loop, you have to have a loop so that the current flows. It gives me a magnetic moment, which is I times its area, A. However, interesting question still arises: do magnetic monopoles exist? And this is a question people still talk about. And for example, as late as in 2016, there is a paper, a review kind of paper or a discussion paper in Physics Today, which is the search for magnetic monopole. This is by A. Rajantia, Physics Today, volume 69, page number 40, 2016. So, you see, even in 21st century people are talking about it, and a lot of people have been interested. Dirac gave a fantastic argument. Our own Meghnad Sahab gave an argument about magnetic monopoles. So, this lecture is about exploring how Maxwell's equations would be modified if magnetic monopoles existed, and how we can detect them, how Lorentz force acts on them, and so on. So, let us begin with the Maxwell's equations that we have learned so far, and they are: divergence of the electric field is charge density over epsilon 0. Then we have curl of E, which is minus partial derivative of t. The integral forms also, let me write, this integral form is E dot ds is q enclosed by epsilon 0, and the integral form of the other one is that integral over a closed path E dot dl is equal to minus d phi b over dt. Then related to this is also something called the motional EMF, which arises from Lorentz force on charges. So, these are the first two Maxwell's equations. Then we have divergence of B is equal to 0, which basically tells you that there are no monopoles. The lines close on themselves, and its integral form is integral B dot ds is equal to 0. The curl equation for this is curl of B is equal to mu naught j plus mu naught epsilon naught dE dt. The integral equation would be integral of B dot ds is equal to mu naught I enclosed, and I am also going to write this as mu naught I displacement. That is the integral form. What about if monopoles existed? What we mean is magnetic monopole. So, in that case, the equation for E does not get affected, because this depends on the divergence depends only on the charge density. However, the curl equation would be modified, because now there is a possibility of a magnetic current. Just like charge current gives rise to a magnetic field, a magnetic current would give rise to an electrical field. Similarly, now divergence of B will not be 0, because now monopoles are there, and we will just say that by symmetry this will be mu times rho magnetic. I am going to write M for this magnetic. And the final equation, which is all consistent, all the charge conservation is there and all that, that remains the same, which is del cross B is equal to mu 0 j charge plus mu 0 epsilon 0 dE dt. So, the equations on which I have to now pay attention are this one gets modified and this one is modified, and we will just focus on those right now. So, let us see if we have divergence of B equals mu 0 rho m, this would also imply that B dot ds is equal to mu naught times q magnetic enclosed by the surface over which I am integrating. So, this would be the Gauss's law for magnetism when magnetic monopoles exist. Let us look at the other equation, and we will just do it systematically. The other equation which I am looking at is curl of E is equal to minus dB dt, and I want to add some term which gives me the magnetic current. And as in the case of displacement current, we will use those kind of arguments. All right. So, let us do that. If I take divergence of curl, this is identically 0, and this should be equal to minus divergence of dB dt plus whatever that extra term is, which is equal to, I will switch the time and space derivatives, d by dt of divergence of B plus whatever that extra term is. And divergence of B we just proposed is nothing but mu naught rho m. So, this is going to be minus mu naught d rho m dt plus this extra term. And this one in time dependent situation is not necessarily 0. So, I have to add something to satisfy the mathematical identity, because left hand side no matter what is going to be 0. This is what gave rise to displacement current earlier. So, let me just ask you to recall, there we had curl of B is equal to mu 0 j plus the extra term that I was looking for. Here I have this term dB dt, I am looking for something corresponding to mu naught j, and what we had there was that divergence of curl of B, which was identically 0, is equal to mu 0 divergence of j plus whatever that extra term I am looking for, and by continuity equation this was equal to minus mu 0 d rho by dt plus that extra term. So, I added d by dt in this. So, before I proceed, I will throw this question at you: what will be the continuity equation, which is also the magnetic charge conservation equation for rho m, and let us call this magnetic current J m. And it is this continuity equation which I am going to use to write that extra thing. Once you write that continuity equation, what you are going to get is that curl of E is going to come out to be minus dB dt minus mu naught J m. I will leave it for you to work it out, look through the continuity equation. So, the 4 Maxwell's equations now are divergence of E equals rho over epsilon 0, curl of E is minus dB dt minus mu 0 j m. Then I have divergence of B is equal to mu 0 rho m, and finally, the fourth equation, which is curl of B is equal to mu 0 j plus epsilon 0 mu 0 dE dt. Let me again throw a question at you, and that is, what will be force law between two magnetic charges Q m1 and Q m2. Once I have these 4 equations, I can now say that interpretation wise, the equation curl of E equals minus dB dt minus mu 0 j m, where it tells us that magnetic current j m gives rise to an electric field, just like charge current gave rise to a magnetic field, right. And this is also in addition plus changing magnetic field or change in flux gives rise to electric field. So, that is dB dt is like the displacement current for E, displacement current of magnetic field, and J m is the magnetic current, magnetic charges are flowing. So, again let me ask you a question, what will be the Biot-Savart law for electric field generated by a magnetic current? Next question that we address is, what will be the Lorentz force on a magnetic charge? Recall that for an electric charge Q, the force is given by Q E plus V cross B. And from the similarity on equations, we would expect something similar for magnetic charges also. For example, the static force on a magnetic charge F, let me write it M, would be Q m B, and is the second term that I am looking for. Let us get it in as simple a way as possible. I will go very closely to the first equation, that is a force on an electric charge, and try to bring an analogy from that. So, let us look at this equation. F equals Q E plus Q V cross B. And let us see how I can see the effect of this. One possible way I can think of this is, this gives rise to motional EMF, and therefore, can be related to d phi b dt, and we will use that analogy. So, the simplest circuit that I can think of is, if I have a circuit and a metallic bar on it, and suppose there is this B field coming out, this is B, and this bar is being pulled with speed v. Then I know that integration E dot dl comes out to be minus d phi b by dt, which in this case is v b l, where L is the length of this rod which is moving. And that is the calculation you have done many times, and this can be related to Lorentz force V cross B. Right. So, what happens when this is moving out? V cross B gives a force which is downward, and therefore, there is a current set up like this. So, EMF I can say is like clockwise in this case, and this is related to that minus sign which I am going to put now in front of this VBL. So, as the flux increases, the current is such that it tries to decrease the flux. Let us now look at the magnetic counterpart. So, what I will do for magnetic counterpart is again make this circuit, put a bar. From the equations, from relationship to the Faraday's law and all that, I expect there will be a V cross B term, and that is what I want to determine now, and let there be an E coming out, and let this bar be pulled to the right with speed V. So, let us understand this. So, for the magnetic counterpart, what I am doing is I have this circuit on which I have put this bar in which the magnetic charges can move. There is this electric field coming out, and this is being pulled to the right with speed v or velocity v. Now, the relevant equation here, counterpart of Faraday's law, is going to be curl of B is equal to mu 0 epsilon 0 dE dt. That is because there is no charge current, and the integral form is going to be integral B dot dl is equal to mu 0 epsilon 0 d by dt of flux due to the electric field phi e, and this is going to be mu 0 epsilon 0 v e L, where L is the length of this rod. What about the sense? You see, now there is no minus sign in front, and therefore, what I expect is that the magnetic charges would be moving clockwise. So, I am going to put that sense out here. This is same as V over C square E L, exactly the same as in the case of Faraday's law, except that B and E are now exchanged. And therefore, I can safely say that the force on a magnetic charge due to electric field is going to be Q m V cross E over C square, but with a minus sign. So, let us see if that works out. You see, in this circuit, the current is moving clockwise, V is to the right, E is coming out. So, V cross E is taking it down. I think I made a mistake, because this is a plus sign. The sign I made automatically was that for the charge current, in this case the direction is going to be opposite. Let me correct myself. I will cut this and make the current, it is counterclockwise, right. So, here also we will make this, cut this, and the current is counterclockwise. So, let us correct ourselves. So, here too the current is counterclockwise, and that minus V cross E is going to be pointing up. So, this will make the current go counterclockwise. Therefore, the full Lorentz force now on a moving magnetic charge is going to be Q m B minus V over C square cross E. So, now we have gotten everything to work out things if there are magnetic and electric charges both. So, let us write them all together. So, we have the Maxwell's equations, divergence of E is equal to 0, curl of E is equal to minus dV dt minus mu naught J m. I have divergence of E is rho over epsilon 0, divergence of B is mu 0 rho m, and curl of B is mu 0 J plus mu 0 epsilon 0 dE dt, and the Lorentz force F equals Q m B minus V over C square E. What I like you to do is develop the argument given above for a general circuit. That means there is a general circuit and it is moving, just like we did when we showed the equivalence of Faraday's law to moving circuit EMF or the motional EMF. So, we have gotten everything that we need for getting, doing mathematics with magnetic monopoles also. Now, I raise two questions, and those are: how do we detect magnetic monopoles? So, what one would do is, you see magnetic monopoles, when they move, there is this flux changing. So, if I take a ring and let a magnetic monopole pass through this, the flux that is there will change, and when it passes the ring and goes to the other side, the flux changes by a huge amount, and this will induce a current in this. And if this ring is made superconducting, this current will sustain if the resistance of the ring is 0. So, only effects are inductive, that is L is not equal to 0. If R was large, then we could have ignored the inductive effects, but now only inductive effects come in. So, I can calculate the current. I will give you this as an assignment problem, and then by measuring that current, you can actually figure out what is the size of that monopole. The other question I am going to address now in a very simple manner is how large or small is magnetic monopole. Is there a limit to it? The question is relevant because the electron is the basic quantum of charge, free charge if you like, because quarks are also there with 1/3 the charge, but free charge electron is the basic quantum. Is there a quantum for monopole? And this answer was given using quantum mechanics. Meghnad Saha himself contributed to it, and I will just give his argument. And the argument is Suppose I have a magnetic monopole Q m and an electron going around it in an orbit. Then the equation of motion, which is m v square over r, will be equal to F Lorentz on electron. And the Bohr quantization condition gives Q m times E equal to some constant, and that fixes the charge Q m. So, again I leave a question for you. What is the value, smallest value of Q m? This argument was made much more sophisticated by Dirac, and this is discussed in the book by Jackson. So, I now stop on the subject of monopoles. Just wanted to give you a flavor of what all it involves, how we look at the equations, how we develop equations if we assume there is a monopole, and I got you all the equations related to monopole, right. So, finally, to conclude, idea of magnetic monopoles was introduced, to corresponding Maxwell's equations written, and so was the Lorentz force equation given, and finally, we discussed some discussion on the detection and magnitude of magnetic charge. Thank you.